Okay, now let's wrap up our discussion here by considering which of these reactions are redox reactions. Okay, so so first thing, this you may look at this reaction and be like, oh, what's going on here? And some reactions you may be able to spot it without assigning oxidation states. But in any case, we should probably assign oxidation numbers in each element. Okay, so for the reactants, let's go here. Let's assign it here. So I'll write it like this. So for the reactants, so we have the reaction between phosphoric acid and liquid ammonia reacting to form ammonium dihydrogen phosphate. Okay, so reactants. So for H3PO4, so we have H3PO4, we have the hydrogen, the phosphorus, and the oxygen. Okay. So remember, oxygen in any compound, -2, that's the easy one. And then hydrogen, so phosphoric acid. So in this case, neither element are metals. So we can say hydrogen should be +1. Okay. So now we have +1 times 3 plus 4 times -2, and we need to find the value for P that will equal 0. So in this case, we have 3 plus -8 plus phosphorus equals 0. So phosphorus should be +5, right? Because -8 plus 3 gives us -5, so phosphorus should be +5. In this case, phosphorus is +5. Now, if we look for ammonia here, we have N and H. Maybe we should line up the H's so we can look at them. So for the ammonia case, hydrogen still +1, but nitrogen here will be -3 because nitrogen is more electronegative than hydrogen, so it'll have -3 to cancel out the +3 that's being contributed from the +1 oxidation state for each hydrogen atom. Okay, so that's the product reactants. Now let's look at the products where it looks, if you think about it, it looks like a synthesis reaction because you're forming an adduct between ammonia and phosphoric acid. Okay, so let's look at H. Phosphorus, oxygen, and let's put nitrogen over here. Okay, so hydrogen, it will probably still be +1. Oxygen still probably -2, right? So now phosphorus and nitrogen still could have different oxidation numbers, so we can't rule out an oxidation reduction reaction just yet. So phosphorus in this case, we don't know what phosphorus could be, but another way we could write this is NH4 plus and then H2PO4 minus. So that might be a little bit easier to kind of realize because if we don't know the oxidation state of nitrogen or phosphorus, it's going to make determining the other one a little bit difficult. So this will be 2 minus. Okay. Oh, sorry, not 2 minus, minus. Okay. So in this case, oxygen still is -2, right? And then there's 2 hydrogens, but we need still to maintain a negative charge. So the only way that's possible is if we have still a total of -1, phosphorus is still going to be +5. Because if we think of it this way, 2 times 1 plus 5 plus 2 times not 2, sorry, 4. 4 times negative 2 equals negative 1, right? Because that's going to be 5 plus 2 is 7, plus negative 8, negative 1, so it matches the charge, so plus 5 is right for phosphorus. Now, for nitrogen's case, there's still going to be a plus 1 for hydrogen, right? So there's going to be a 4 times 1 plus nitrogen, which equals positive 1 this time. Okay? So what should nitrogen be? Well, in this case, nitrogen should just still be negative 3 because that will give us a negative 1 value. A total of positive 1 for the ion. So nitrogen here is going to be negative 3 if we subtract both sides by 4. So nitrogen is still negative 3 here in this case. So in this case, nitrogen is negative 3. Phosphorus is still positive 5. So this is not a redox reaction. Not a redox reaction. Because if we think about it, the hydrogen stay the same here. So still plus 1. Phosphorus is still plus 5. Nitrogen is still negative 3. Oxygen is still negative 2. So all the atoms have the same oxidation state before the reaction and after the reaction. So they are not, this is not a redox reaction. Okay, now let's go on to the next one. All right, so we have ammonia reacting with oxygen to give us nitrogen oxide plus 6H2O. Okay, so this one, let's do the same thing here. So we're going to have N and H on the ammonia side. Oxygen will have oxygen here. And then for this side, we have N, O, and then H and O for water. Okay. So on the left side, nitrogen, we kind of calculated that in the previous example is going to be negative 3. Hydrogen is going to be positive 1. And then oxygen here is not going to be negative 2. It's oxygen in its elemental form. So it's going to be 0. Now, let's look at NO. So in this case, oxygen now will have a negative 2 charge. And then by default, since it's only NO, nitrogen should be plus 2 to cancel out the negative 2. Like that. Okay? And in this case, hydrogen is still going to be plus 1 in water, and then oxygen here is going to be negative 2. So now we have a situation where 2 of the oxidation numbers are different for 2 atoms in our chemical reaction. So here we see that nitrogen is going from negative 3 to positive 2. So it's going from negative 3, so nitrogen, negative 3 to positive 2. So this is being, so this means it's oxidized. So nitrogen is being oxidized. Okay? And for oxygen, we see it's going from 0. So maybe we could draw an arrow here. Sorry, it's kind of roundabout way here. It's going from 0 to negative 2. So it's being reduced. So this combustion reaction is an oxidation process. And you could kind of tell right away if you react anything with just molecular oxygen, that's a combustion, and all combustion reactions are redox reactions. They should never be anything else but redox reactions. So this is yes. This is a redox reaction. Okay, so this is a redox reaction. Okay, let's do the last one, and I think I'll end it. Um, I think I'll end it, or maybe I don't think we should need more time, but I could do one more example after this one, just for good measure. Okay. All right. So yeah, I could do another one. I have another one in mind. I think that's pretty cool. Okay, so now we're taking liquid methanol. Well, sorry, methanol is always a liquid. Methanol. So CH3OH is methanol, the simplest alcohol, plus carbon monoxide. Interesting. This is how you can make acetic acid. You can take CO gas and pressurize it under methanol, and eventually, with the help of a metal catalyst, and you can make acetic acid. So usually that's how acetic acid is made, by carbonylation of methanol. That's like the cheapest way to make acetic acid. Interesting enough, we can actually get acetic acid from biomass. So if you take like bio, I would say bio mass raw material, like grass, wood chips, any kind of like wooding or wood from maybe from burnt up trees, or from recycled land or something, trees that were removed. You can actually convert it to acetic acid using chemistry as well. So it's kind of like, oh, okay, we get this liquid fuel, right? Like acetic acid is not a fuel, but it's a food additive. We can actually get acetic acid from wood, so that may not seem possible. It may even seem like magic, but there is some science behind it, and it's not. It looks like magic, but it's not magic. So we can actually explain how we got there. So that's an active area of research, like replacing like methanol. You can pretty much get methanol. Methanol also comes from like oil, so like oil feedstocks. But we're trying to replace that, because eventually all the oil will probably run out. And then once that happens, it'll probably nosedive our economy into some kind of recession. And we don't want that to happen. So we're trying to branch out our energy, consumption into different areas. So chemistry will play a pretty important role in the future. Even more so for green chemistry, which makes chemistry even a lot harder to do, because there's certain limitations you can't do, right? But anyway, let's not detract any further. If anyone has any interest in the topic, I'll be glad to talk about it outside of class, okay? But just trying to relate everything back to like the world around us. Remember, chemistry, I think, is best science. Everything around us is chemistry. The air we breathe, the food we intake, and pretty much how things work around our lives. Chemistry plays a very important role. Okay, so for methanol, let's go see here. So for carbon, hydrogen, oxygen. So remember, in this case, we can't say that we need to first think about the oxidation states here. Okay, so if we know hydrogen is +1, right? And then oxygen should be -2. Now, if we add those two numbers up, we will get 4 times +1 plus -2, now plus carbon equals 0. So carbon should be -2, right? Because 4 plus -2 is still -2. So, sorry, not -2, +2. So to get back to 0, carbon should be -2. All right, and then in this example, carbon monoxide, oxygen is going to be -2, but carbon in this case is going to be +2 to cancel out and get a neutral a neutral charge for, or no charge for the molecule. Now this is now acetic acid again. So remember acetic acid here. So now we have two different carbon atoms. So let's label this carbon 1. So this will be carbon 1. This will be carbon 2. We have carbon 1, and then we also have carbon 2. And then we have hydrogen and oxygen. So in this case, we have to assign the oxidation states a little bit different for carbon. So hydrogen is +1 again, and oxygen is still -2. Now we need to determine the individual carbon oxidation states. So remember, in carbon 1, so for C1, we have C1 plus 3 times +1 for all the hydrogen atoms equals to 0, right? So we don't consider carbon because it does not affect the oxidation state of a next door carbon atom, so we don't consider that one. So in this case, carbon 1 must be -3, right, to cancel the +3. And that's what we determined in our procedure a few pages up. Okay, carbon 2. Now we take carbon 2, it's next to the double bond O, and it has, so carbon 2, the H is not attached to the carbon, so that's not going to influence the structure. So let's just redraw the structure here. CH3, so all the carbons, all the hydrogens are attached there. And then here is the central carbon atom attached to a double bonded oxygen and an OH bond here. Okay, so we look at the second carbon atom. So this is C2, and this is going to be C1. We see here that for carbon 2, it's attached to it has 3 bonds to oxygen, right? So we're going to say that that it's going to be it's going to have an oxidation state where there's going to be a plus charge on the oxygen atoms, right? So remember how we separated the bonds, split up the electrons. So what we say here is that carbon, so maybe we should do it a little differently. So there we will use the formula, right? So carbon now, we would rewrite this as H3C, and then replace the electrons here. Now carbon has no more electrons, and then the hydrogen, the oxygen here will have mainly all the electrons associated with it, the oxygen. Okay, and then we circle here. We have only 1 electron around this carbon atom, so we say 4 for the valence number of electrons, minus 1 gives us +3. So here's the valence electrons on carbon 2. Here are the number of electrons on carbon 2, around carbon 2, based on our model. So we get a value of +3, so carbon 2 should have a value of +3. Okay? So if we look here, carbon, so if we look at carbon 1, so hydrogen in both cases not changing, oxygen's not changing, but 2 of the carbon atoms are changing, right? So for carbon 1, so if we think about the CH3, right, okay. So look at these carbons. So that's number 2. I just got a little bit confused here. So look at carbon 1. Carbon 1 is going from -2 to -3. So carbon 1 is getting oxidized. So carbon is oxidized. So carbon is oxidized. And then carbon 2, we see it's going from +2. So no, carbon 1 is reduced. Sorry, it should say reduced. Because it's getting lower in oxidation state. And then carbon 2 here is going from +2 to +3. So you see right here, +2 to +3. Carbon 2 is oxidized. So even though we don't have, we have the same element is both being reduced and oxidized, that's okay because there's two different types of carbon atoms. So it's fine to say, oh, okay, one's being reduced and one's being oxidized. Okay, so this is also a redox reaction. Okay, so that is also a redox reaction. Okay, so let me just put in parentheses here. It's going from -2 to -3. And this one's going from +2 to +3. Okay? All right, so that's our discussion on redox reactions. I don't have time to go over the extra example, but if students want to go over more, the discussion will help prepare for that. And also, there'll probably be at least a future quiz on this stuff. So we'll get more practice testing ourselves. And then there's practice problems also posted on Canvas that can help with this redox chemistry. Okay, so that's our discussion, our lecture on oxidation reduction reactions. This is pretty much all you need to know. Calculating oxidation number and predicting if something's a redox reaction. And then next lecture we'll start our discussion on acid-base chemistry. Okay, all right. See you next time.